It's a great pleasure to have Simone Warzel here in our AQFP seminar, and I'd like to introduce her briefly. Simone studied in Erlangen, Nuremberg, and also at Cambridge, where she did a mathematics tripos. She then did her PhD under the supervision of Hajo Leschke in Erlangen. And as far as I learned from his webpage, this makes you the great-great-great-granddaughter of Sommerfeld in an academic sense, and the great to the power 8 granddaughter of Gauss. Well, Simone has many achievements of her own. Let me continue with her CV. She after some more time in Erlangen, she went directly to Princeton University, where she spent 5 years working with Michael Eisenman, who is also present, and then returned, followed a call to TU München as a professor in the mathematics department. She has, however, been affiliated to Princeton University for, I think, 10 more years, approximately, as an international scholar. She has received many distinctions. Her field of work is quantum mechanics in connection to randomness. She has done a lot of work on Lifshitz tails in magnetic fields, then important work on the famous problem of extended states and absolutely continuous spectrum for random operators, in particular on trees and augmented trees, and many other things, localization in many particle systems. And today she's going to tell us about quantum spin glasses, another hard problem. Please go ahead, Simone.
Thanks very much, Manfred, for this kind introduction. So I actually designed the talk for non-experts, and I'm a bit ashamed that I see so many experts in the audience. So, you know, I'd be telling you things which you anyway know. So the way I thought about going about this topic is, in my first part, I just basically want to tell you why this field might be interesting. And to do that, I actually want to start recalling a few basic things about classical mean field glass models. And the Drosophila of all models is, of course, the Sherrington-Kirkpatrick model. So what is the Sherrington-Kirkpatrick model? We imagine n Ising spins. So that's just binary variables. And we couple those Ising spins, every Ising spin with every other Ising spin, in a mean field way, and the couplings will be chosen randomly. And it's customary if we choose a Gaussian distribution. What's important is mean zero, and they are normalized to 1, so that when you divide this mean field interaction, which is random, by 1/√n, the energy lives on order n, like the number of Ising spins, which we have here. Okay, so of course, that's not the only mean field model which is available, also not the only mean field coupling in which you can imagine on Ising spins. We could look at more general p-spin couplings. That is to say, that we just take interactions which involve p of those n Ising spins, and let everybody of these p sets interact with everybody else, and then you have to normalize again properly so that your total energy lives on order n. In my talk, a particular limit will play a role, and we just to explain to you the basics, and that's the famous random energy model. That is the limit p tending to infinity, and a proper way to describe that is as follows. After all, what we are describing here is a random Gaussian field on the hypercube of Ising spin configurations. And it's a Gaussian field which is described by first and second moment. I mean, the first moment I always choose 0, so I didn't write it. In the second moment, of course, that's now a correlated Gaussian field in case of the Sherrington-Kirkpatrick model, because the correlations, although these things here are IID, of course, the field on the hypercube is then strongly correlated. P tending to infinity is the uncorrelated limit in which if you take one Ising spin configuration and another Ising spin configuration, sigma primed, the correlations here vanish unless they are both equal. All right. Now, why should you be interested in such problems? Well, I mean, these Gaussian random fields are kind of the prototypes of rugged energy landscapes with built-in frustration. Why frustration? Well, because we have a spin model where randomly you either have a ferromagnetic coupling. If you think about it, we sort of P equal to 2 again. If G is positive, then of course, if the two spins want to align, and if G is negative, the two spins want to anti-align. And since sort of everybody is coupled to everybody else, you immediately get into a frustrated system. So in these systems, of course, already seemingly simple questions like what is the minimum in this rugged energy landscape and how does the minimum configuration look like are complex problems. And there's a great deal of research devoted to finding algorithms which run in polynomial runtime to, for example, find the minimum in the famous Sherrington-Kirkpatrick model. And very recently, Montanari came up with exactly such an algorithm, at least finding the minimum up to sort of epsilon precision. Now, I don't come from computer science, as you know. I come more from statistical mechanics, and in statistical mechanics, these systems came up as kind of the prototype systems for ergodicity breaking, and a very interesting kind of ergodicity breaking in statistical mechanics. So what does one look at? One looks, of course, at the free energy or negative free energy. There's, of course, a factor of minus and 1 over beta missing if you're a physicist. And the interesting phenomenon which happens in these classes is that there's a freezing transition. So there's a phase transition. And on top of that, the Gibbs measure exhibits an interesting structure. Okay, and all of that was described by Parisi in his famous works, which actually recently received the Nobel Prize. Now, since I assume maybe that not everybody here has seen a spin glass freezing transition, so let me try to explain the basics. So what is this phase transition? So let's go a bit to the simplest example of the random energy model. I've eliminated my silly coupling constant here. And let's try to determine the partition function. So I'm writing trace here, although I'm in classical statistical mechanics, by which I just mean the sum over all configurations. So what would be the partition function of the random energy model? Well, that's a seemingly simple problem, you could say. So I'm just for convenience, I'm normalizing my partition function by the number of configurations which are available in these n Ising systems, which is 2 to the n. And then the question, what's the partition function, looks like the question, I'm going to just evaluate a huge sum of independent random variables. Then the law of large numbers suggests, as you know, that this is very strongly concentrated near the average, and the average is easily computable. After all, it's a Gaussian random field, and so that's the outcome. Okay, now what's wrong? Of course, that's not the correct answer always, because there's a small print in the law of large numbers. And the small print is of course, that it could be that this huge sum is dominated by the large deviations and the large negative deviations of this random energy model. Okay, so first of all, what do we know about the large negative deviations? As I said, my scaling here is such that the maximum and minimum of this Gaussian random field lives on order n. And if you ask me I have now 2 to the n independent random variables with a covariance n, where is the almost to a maximum? Well, that's computable, and that's this magic number beta c, which will appear throughout my talk. Okay, so and depending on whether the inverse temperature beta is now larger or smaller than this magic value, you're either in the domain of validity of the law of large numbers, that's for small beta, or if beta is larger, then this sum is heavily dominated by the large deviations, and then the free energy or the negative free energy, which I call pressure, is then just given by a linear behavior, where the beta c is exactly kind of the scale of the minimum of the REM. Okay, and that's what you see here is kind of the Drosophila, or the simplest example of this freezing transition. Okay, where you see a linear behavior in beta. Okay, so now in more general spin models, which I've just flashed on my first transparencies, like the SK model, a similar phenomenon happens, but of course the description of what happens there is a bit more involved, and the full description is in terms of Parisi's formula, and we'll come back to that. Now, one thing which you should bear in mind is that this is just a first attempt of trying to approach what happens in spin glasses. Of course, what we want to know is kind of what's the structure of the full Gibbs measure. And Parisi tells us how you should think about this full Gibbs measure, and even kind of from this point of view of standard theoretical physics, if you have a phase transition, you ask about the order parameter. Now, these are magnetic systems, and so you could think, there's magnetization, but of course, since there's no direction which is favored in this system, there is no magnetization transition which comes along with this freezing transition. What is going on here really is that this system fractures into many parts, and in each of those parts it has kind of its own magnetization. And the correct order parameter, which in the end we know describes the full system, is in fact this distribution of the so-called replica overlap. So what is this replica overlap? There you make the Gedanken experiment that you duplicate the system, take on 2 copies of your Ising variables the same randomness, and then under this duplicated Gibbs measure, ask about the distribution of this observable. Okay, and what we figure out is that the distribution of this observable is kind of, it's not a delta function if you go below the freezing temperature, but this replica overlap can take sort of many values, and these many values describe, so to say, each of these thermodynamic states which are realized. So this is the famous description of ergodicity breaking in a spin glass. Now you can ask if you sort of, maybe that's a bit crazy if you're an experimentalist, and how should I ever get a hold on the replica overlap? Now, what physicists usually measure is the so-called Edwards-Anderson order parameter. That is basically sort of a susceptibility. So what you do is, since it's a mean field system, you just take two Ising spins, J and at K, you average, and you average the mean square of that. I mean, that's the Edwards-Anderson order parameter, which you can then convince yourself, I mean, it's very easy, that's nothing is but the average of the square of the replica overlap. So if there's a non-trivial value of the distribution of the replica overlap, you will see this in a non-zero value of the Edwards-Anderson parameter. And of course, everything is random. I mean, in order to come up with a simple quantity, one can just take the disorder average. So the average of over all of those thermodynamic states. Okay, so this is kind of a natural order parameter to monitor. Now, I'll give a bit of more details of how you describe the Gibbs measure later, but let me now come to my main topic. I mean, that would be quantum spin glasses. So what are quantum spin glasses? Well, there's a huge pot of models which you can look at, and what I'm interested in is studying transverse field models. So now I promote the Ising variables in its simplest way to spin 1/2 operators. And so my preferred basis, where I think of recording the spin 1/2 quantities, is the Z basis. And then I can take my favorite rugged energy landscape. So for example, this P spin glass, P is equal to 2, and it would correspond to the Sherrington-Kirkpatrick glass. And insert the commuting variables of those Z components of the spin 1/2. Okay, so if I would just look at that, I mean, that's of course a classical model. I mean, there's nothing quantum about it. It's diagonal in the Z basis. To make it quantum, I add a transversal magnetic field. Transversal meaning, so I just pick another direction. I will pick the X direction and add a constant magnetic field. And the way you describe this is you just take your SX spin matrix acting on the J's particle and just sum overall particles. And B is really then the strength of the magnetic field. So this, of course, the natural Hilbert space on which this acts is the tensor product of the simple C2, which is the Hilbert space of one spin half entity. There's another way to think about this. If you take the Z basis as the canonical basis of this tensor product Hilbert space, then you can think of this just as a vector of 2 to the n components, because that's the dimension of this Hilbert space. And each of those components then can take values plus or minus 1. That's kind of the natural values of sigma Z. Okay, and so in this way, I'm defining a class of transversal field models depending on what kind of classical spin glass I want to quantize by this procedure. Notice the following, that if I take the simplest spin glass, where I could easily calculate the classical partition function, which was the random energy model, then what do I get? Well, I get kind of in the canonical basis, I can think of this Hamiltonian here as a random matrix which has on the diagonals independent identically distributed values for p equal to infinity. And then what does that term do? Well, you know, sigma x now flips the z spin, right? So if you think about what this term represents on my canonical basis vector, it can now flip one of those n components. Okay. So that is another perspective to look at that. And if you look at this Hamiltonian from this perspective, really what you have is the Anderson model with a Gaussian random field for p equal to infinity and defined on a graph where I promote now my hypercube to the usual graph hypercube by assigning to each vertex its n canonical neighbors which result from one spin flip. And then this operator here is nothing else but the adjacency matrix on that graph. Okay, so for p equal to infinity, I mean, what I really have here is a 2 to the n by 2 to the n matrix, which I can call the Anderson model on the hypercube. Now, if I go to a more interesting spin glass model, like the quantum Sherrington-Kirkpatrick model, it's not anymore the canonical Anderson model in the sense that my random potential, which is that term here, is now heavily correlated. Okay, that's another perspective to look at these quantities. Now, so why would I do this? I mean, there are many motivations for looking at these type of operators. So first of all, there's the intrinsic question. Now there are these interesting classical spin glass models. We've seen with their phase transitions. There's a spin glass phase, which has interesting features, as I will also try to describe later. And what happens to the spin glass phase if I turn on a magnetic field? That's kind of even a classical question. If I turn on a longitudinal field, which would be the constant field in the z direction, and what I'm doing is I'm turning on now this transversal field, but I'm not the first one. In fact, way before Parisi published his famous papers, Bray and Moore, we already asked the question, what happens, for example, to the classical Sherrington-Kirkpatrick description if I now turn on a transversal field? Okay, so in mathematics, mostly kind of the story about the longitudinal fields, which goes under the name kind of Almeida-Thouless line, is discussed. But in physics, sort of at the very same time, people already asked me the quantum question. Now, so you might think of it, that's very old in physics, and what's there to still figure out? I mean, well, first of all, of course, that's a hard question. It's even a hard question on the classical level. But more recently, people woke up to these type of models because, in some sense, as I said, spin glasses represent kind of a Drosophila for ergodicity breaking. And now there's the question of what happens to ergodicity breaking in quantum models. There's the huge discussion about many-body localization, and in general, how quantum ergodicity can be broken or not. And these models receive quite a lot of attention, even these days in the physics literature. Now, I have to say, I mean, that this is a very small corner of the universe of quantum spin glasses, and there's other spin glasses which are not mean field type, which physicists look at, like the Heisenberg spin glass. But there are also models which I've kind of discussed, I mean, even in relation to black hole physics, which is this famous Sartefi-Kitaev model. where you can also discuss things similar, namely breaking of quantum ergodicity, existence of replica symmetry breaking, and so on. Okay, so I've already alluded to the fact that there are various lenses through which I can analyze this very random matrix of my transversal field models. I would either look at the statistical mechanical lens, where I would try to figure out what happens to the phases, which I see classically in quantum mechanics. So the interesting quantity would be the free energy, the pressure, defined in terms of the quantum partition function. And then, of course, the order parameter. So is there kind of still replica symmetry breaking? So what happens to the old Parisi type of replica symmetry breaking order, where I do the same thing? I duplicate the system and ask me what happens now to this quantum observable. As I also already alluded, there's another perspective where another level of the description which I could focus into, and that would be the level of looking at this beast as a random matrix of a particular type, namely of Anderson type with correlations. And then you would be interested in spectral and localization properties of eigenvectors. Okay, so that's a bit more detailed description. These questions are not only of interest to the community of people who are interested in Anderson localization, but remarkably also to mathematical biologists, because after all, semi-groups of that type play a role in descriptions of simplistic models of genetics, where the magnetic field induces these spin flips, and that's the mutation of these genotypes. And the U, kind of this part here, would be the fitness landscape. And then in the end, what you would what you'd be interested in is, in fact, the long time behavior of the semi-group. And as we all know, the long time behavior of the semi-group, that's dominated by the ground state and the properties of the ground state eigenvector. Okay, so figuring out how the localization properties of these random matrices look like is also of interest to this community. And then, since I've stated it on one of my slides, I mentioned that these are hard optimization problem. Of course, there is an interest in quantum information in these type of Hamiltonians, actually in adiabatic switches between the transversal field part and the kind of rugged energy landscape part, to figure out whether kind of the natural quantum evolution we could do the optimization problem. And that goes under the name of quantum optimization. I think I probably won't have time too much to talk about that. So let me start by telling you results which we obtained through the lens of statistical mechanics, where kind of the motivation is what happens to the old freezing transition, what happens to replica symmetry breaking if I now switch on this transversal field, this part of quantum mechanics. Okay, as I said, the most important model is the quantum Sherrington-Kirkpatrick model. That's kind of the Drosophila. What I've plotted here is temperature versus magnetic field in natural units. And if you switch off the transversal field, then you will see the old freezing transition here at temperature in units 1. So that's high temperature and that's low temperature. And where it is known, for example, by this explicit parisi formula, but also earlier by an argument which I'll show you in a second, that there is replica symmetry breaking in this parameter regime, and there's no replica symmetry breaking in this parameter regime. And that's where the phase transition happens. Okay, what physicists believe, and that's the gray cartoon here, is that the spin glass phase in the presence of a magnetic field extends to the gray area, and that's the phase transition then towards a paramagnet, where you lose the glassiness. Okay, now, unfortunately, I mean, that's kind of the difficulty in the story, is that there is no quantum parisi formula, at least not for the quantum Sherrington-Kirkpatrick model. You can write down variational problems, but these are not anymore analyzable as the variational problem which you started from, the Gibbs variational problem. So here's the theorem which we can prove, and that's a work together, funnily, with my advisor and two students. So what we managed to prove is that there is a parameter regime of at least small transversal field, and that's the red parameter regime, which extends really up to the transition point at zero field, where we can prove that replica symmetry breaking survives. Remember, there's this Edwards-Anderson order parameter, which is the average of the replica overlap, which happens to be just the expected value. That's the disorder expected value, and the brackets here are just the Gibbs expected values of two spins. And it doesn't matter which two we take. We can take the first and the second, because it's anyway a mean field model, and you square it. Okay, and what we can prove is that in the red region, we still have replica symmetry breaking. Now, what was known from an earlier paper is that in the blue region, there's no replica symmetry breaking. Okay, so at least somehow this establishes that there is a phase transition even in the presence of transversal fields. Now, since no talk, so maybe to the experts in the audience, kind of in the old classical regime, it was always understood that replica symmetry breaking goes along with losing quench is equal to annealed. That's not longer true in quantum mechanics, just as a warning. Okay, so no talk without a proof, so let me give you the proof. In fact, the proof is so beautifully short that I can give it on 2 slides. And in fact, it is the proof by the old team, by which I mean there was a paper by Bray and Moore in the 80s, and independently, the same argument was rediscovered by Eisenman, Lebowitz, and Well in the 80s, which establishes the existence of replica symmetry breaking in classical models. And here is the argument. Okay, remember the SK model is this mean field model. And we now want to relate, the observation is that you can relate the order parameter, which is this beast, to the mean specific energy. And mean in the double sense, namely disorder averaged and Gibbs averaged. Now it's because of that it's a mean field model, this happens to be equal to just the expected value of just the G12 random variable and the 2-point correlation function. Now you can see that because we are dealing with Gaussians, this screams you have to do an integration by parts. Okay, what happens if you do an integration by parts? Well, you get a 1 and you get a derivative of that beast here with respect to G12. The derivative will consist of 2 parts, right? There's certainly kind of a square popping up, and that's what we want. Namely, that's the order parameter. But then there's another beast which pops up, and I'm writing this too complicated now because I'm preparing for quantum mechanics. It involves this Duhamel-Kubo scalar product of the observable, of which you took the Gibbs expectation. That's the usual differentiation formula. Okay, now that's this Duhamel scalar product, which, so to say, involves this kind of Euclidean time evolved version of A and scalar product with itself. Now, of course, this is way too complicated to write it in classical mechanics, because in classical mechanics everything commutes, right? So you know, it's not there, and then you use that A squared in case of easing variables. I mean, that's 1, right? So this complicated beast here in classical mechanics is just 1. But then that's great, because if there's a 1 here, right, and you tune up beta, so you decrease the temperature, there will suddenly be a regime where the left-hand side here is positive, right, because that's a bounded quantity. Okay, and that's the argument designed by these guys here to prove that there is some replica symmetry breaking at sufficiently low temperatures. Now, how do we understand that this survives quantum mechanically? Well, you know, same calculation. I mean, I've prepared for things to also hold quantum mechanically. Then we have this Duhamel scalar product, but then this Duhamel scalar product, we cannot do the trick with a 1 anymore because nothing commutes here. However, you know, there's the old device which is Falk-Bruch's inequality, by which you estimate this Duhamel scalar product in terms of usual Gibbs expectation values of these double commutators. And these double commutators can be worked out, and what you'll find is this double commutator turns out to be given by an expected value of the transversal field. And this you can estimate if you want by 1, then you just have the B, but you can also sort of work a bit harder and get the hyperbolic tangent. Now, and then we can argue as follows, there's a B appearing here. And for sufficiently small I forgot to mention what this function phi is. This function phi is kind of a relatively boring object. You know, it can be expressed in terms of an exponential, basically asymptotically. But to not bother you with details, the important thing is if I now choose B small enough, right? I suddenly sort of get close to 1, and then I choose beta large, and then there will be something left of this replica symmetry breaking, and that's basically how we get the red regime here. It's a bit simplistic, but you have to work a bit in order to really get there, but that's the idea. Okay, now that we understood that there is still replica symmetry breaking in these systems, we could be a bit more ambitious and ask, do we understand more about the Gibbs measure? And for that, I now want to go back to classical glasses and remind you that there's more to this story about how you describe the Gibbs measure. Namely, part of the interesting story about spin glasses is there's this emergent hierarchical organization characterized by the ultrametricity of the distribution of these replica overlaps. And that's a long story, which is now sort of understood completely in the sense that it is really just this ultrametricity of the distribution of the overlap which characterizes the full classical Gibbs measure. In a bit of a simplistic way, what happens here is that as you tune down the temperature, also in the SK glass, what happens is that groups of spins freeze out, as in the REM, but the freezing out is organized in this hierarchical way. They're really sort of a continuum of temperatures where things freeze out successively. Okay, now it was Derrida's brilliant idea in the 80s to get a grasp of this hierarchical structure to come up with a cartoon. and a cartoon which is a bit less simplistic than the random energy model, where you just have one group of spin, namely either everybody freezes out or not, but you have several groups of spins. So you think about sort of organizing your spins into types. So these are these little vectors here which have a length. And then you devise a model where first the first group freezes out, then the second group freezes out, and so on. It's kind of a bit like operating like a bad mathematician. Physics leaves you with this interesting picture and decides on who freezes out first, and then you pre-assign who freezes out first. So you don't let the model decide who freezes out first, but you pre-assign this. And these are how these cartoon models are designed. That's what's called the generalized random energy model. Formally, what you do is you just linearly combine random energy models, which depend on longer and longer bit strings of these groups of spins. Okay, so another way to describe that is that this is again a Gaussian random field. All of its information is in the covariance, and what characterizes the covariance is a concave function. So I'm cutting the story a bit short, and this concave function now in this formulation can be recovered from these prefactors here of these random energy models. So there's A1 of which square root happens or sits as the first prefactor, and so on. So you can think of it sort of these A's here without loss of generality summing up to 1 and defining this concave function. So basically defining this distribution function and its concave hull. And the freezing in these generalized random energy models, we have to do some analysis, but fortunately, if this was all done, happens then in the following form, that the first group of this concave hull freezes out first. So that's the largest temperature, namely the smallest beta, and then the next group freezes out, and so on. Okay, all right. Now, what we asked ourselves is, so let's entertain for the moment if we somehow taking the generalized random energy model as our classical model, which we want to quantize, where we want to ask what happens if I now add a transversal field. And to our very surprise, the physicists haven't discovered the formula, but we managed to work out a formula for the pressure. So this is, this is analyzable. There is a quantum parisi formula, and here's the quantum parisi formula. Now, the way this works is as follows. So you have a Legendre type transformation where the experts in the audience will immediately recognize this term here. That's the pressure of just the Hamiltonian, where I just strike out U completely. Okay, so that's the quantum paramagnet. And I linearly interpolate between the quantum paramagnet and just the pure classical pressure of just the first group of up to X spins. Okay, there's a formula. I don't want to bother you with this formula. It's long but explicit. In particular, by the way, what's contained in this formula is the special generalized random energy model where the concave hull is just linear, and that's the quantum random energy model, where this is linear and where you see that there's a first order phase transition, because this soup then is very easy. It's either this term or that term, depending on how big beta is. Okay, let me skip that. Everything is generalizable. Let me entertain you what the phase diagrams look like if you work out this variational problem using the explicit formulas. Okay, so of course this depends very much on the model parameters, and let me take a so-called three-step replica symmetry breaking generalized random energy model, meaning that I have a concave hull which consists of 3 slopes. So I have three groups of spins. At this temperature, the green freezes. At this temperature, the blue freezes. At this temperature, the pink freezes. Now you turn on the magnetic field. The magnetic field is this time in this direction. Here, everybody is frozen. And now you tune the magnetic field. Once you cross this level here of the magnetic field, the pink guys, they will flip into paramagnetic order. So they will flip into the Z order. And then if you cross this line, the blue guys will flip. And if you cross this line here, everybody will flip. And then you are at the quantum paramagnet that corresponds to x equal to 0. Okay, that's what's described by this formula. Of course, a three-step replica symmetry breaking, that's not the cartoon of what happens in the quantum Sherrington-Kirkpatrick model. In the Sherrington-Kirkpatrick model, the cartoon of that would be a continuous A, continuous concave A. And you can also maybe sort of plug this into this formula, and then you will, instead of getting these first order phase transition of these n-step replica symmetry breaking model, you will actually get a second order transition. And in here, you kind of have a mixed phase in the sense there is partially you see a magnetization in x direction, and you will only lose the magnetization in x direction once you completely switch off B. But you will still have a spin glass phase down there. Okay, the spin glass phase is lost once you cross the freezing temperature and heat it up. So this is what's described by these quantum parisi formulas. And kind of the take-home message is that, at least in these caricatures, what happens is that there's a quantum erasure of replica symmetry breaking, which you can tune by looking at the different generalized random energy models. And what you see is there are these mixed phases, where part of the system is still frozen in spin glass order, but part of the system is already in the transversal order. Okay, good. Now I have 12 minutes left to give you my third perspective on these models. And I alluded to this. There's reasons why you may want to look at these type of problems also from this perspective of Anderson localization or Anderson delocalization. Now, not surprisingly, this is a more detailed question on how do the energy states look like, how do the eigenvectors of the system look like. It's more detailed than asking just about the free energy and the phase transition. And therefore, it's not surprising that I will resort my analysis to the simplest model, which is this quantum random energy model, where things are uncorrelated. All right. Just as a reminder, what I have really is a random matrix, which is of Anderson type. And as I said, another way to look at these type of quantum spin glasses is to say that I have on my diagonal this random potential, and there's just the adjacency model on the hypercube where I render the Ising spin configurations or the configurations of the Z spins into a graph by connecting vertices which differ only by one spin flip. And that's kind of a cartoon of this hypercube then. Okay, so this vertex, for example, has n neighbors. Okay. All right. So as I said, I mean, we completely know, I mean, what the thermodynamic phase diagram looks like. That's very easy. I mean, that's described to me by a special case of these quantum parisi formulas. We have this first order phase transition. Once I tune up the magnetic field, I've told you how to calculate the free energy without a magnetic field, but now we've also seen sort of how the formulas look like with a magnetic field. And there's the glass phase here. That's just the unfrozen rim, where I don't have transversal order. So there's no transversal magnetic field. And in this phase, there is a transversal magnetic field. Okay, so in some sense, sort of what I want to do is I now want to look at this as a random matrix problem where I want to study, for example, where is the ground state? What kind of features does the ground state eigenvector have in my preferred basis, which is the Z basis? Okay, now from this perspective, it is natural to think about this random energy model as a potential. And that's kind of a cartoon. So think about what I'm drawing here is the hypercube, which is down there. And to every vertex on the hypercube, I assign a random value. And because things are drawn easier, I'm just drawing negative values of the random potential. Of course, the random energy model is symmetric, right? It's a Gaussian random variable. So there would be also deviations up here. So from this Anderson perspective, I'm now walking on the hypercube in a random potential, and this random potential has a bizarre feature. It basically looks like a golf course, namely its typical values, the typical values of this random function here are on order squared of n. This is kind of the noise, and its large deviations are on order n. But these large deviations, if you ask, kind of pick an epsilon, and now on this hypercube, where are the large deviations? And there, if epsilon is strictly positive, spatially separated typically. Okay, so from this point of view, if I ask you, and I hope you're honest, I ask you sort of, what would you guess what the ground state looks like? I'm doing Anderson localization, the ground state will be somewhere there, and of course it will be localized, right? That's of course wrong, because we know what the ground state looks like. That's at 0 temperature. And what this phase diagram tells you is that here you have a glass behavior. So this is consistent with localization, but here you have a quantum paramagnet. That's not consistent with localization. All right. So of course, this was known to physicists quite a bit already. In the end, since I only have time to explain it on a physics level, let me walk you through what's going on here. If you think about sort of how this Hamiltonian here acts in the natural Z basis, so these are the localized states. So delta of X is in this basis on L2 of the hypercube. It is a vector of 2 to the n entries, and it has a 1 exactly at this configuration sigma. Otherwise, it's 0. Okay, so what are the diagonal? What's the expectation of H in my localized basis? Well, there's the potential, and I of course get the potential, but the adjacency matrix doesn't contribute. So if I think about it, sort of a variational ansatz to the ground state, as a guess, this leaves me an energy of just the potential energy, and we've discussed that the minimum of the potential is on order minus beta Cn. That's this magic number, square root of 2 ln2. Okay, so that's one guess. And you could also say, let me take the ground state of the adjacency matrix. What's the ground state of the adjacency matrix? The good physicists know this. This is a constant field, right? So it's in the Z basis. Of course, it's the maximally localized state. And I'm doing the L2 normalization, meaning that I have to do the square root of 1 over 2 to the n. These are 2 to the n entries. Now let's compute somehow as a variational guess what this is. Well, then this guy here will obviously be minus bn, right? And what's that guy? Well, that's just the average value of independent random variables. That's 0. Well, it fluctuates, but it fluctuates on the order of 1 over square root of 2 to the n. That's exponentially small fluctuations. So now you see that in either beta C is bigger than B or it's smaller than B. Then if it's bigger than B, then this is your deeper state, or if it's smaller than this is your deeper state. Right? And now you kind of have an intuitive explanation of how this ground state phase transition works. Right? Because in this regime, you expect the ground state to look more or less like that. And in this regime, you expect the ground state to more or less to look like that. And that's indeed something which we can prove. In fact, we can prove a bit more. We can in fact describe the full spectrum up to order 1 in energy. In the paramagnetic phase, so that's to the right in the phase diagram, up to energies where the smallest value of the potential can so to say reach. What you see here as eigenvalues, so if you just draw the spectrum, right, there's 0. Now the spectrum of the adjacency matrix, this you know what it is, right? That goes in even integers from minus n to n. Okay, so that's the spectrum of just the adjacency matrix. Now what we see here is the spectrum of the adjacency matrix. That's 2n minus nb. Oh, sorry, I forgot b. Everything is in scales of b. Right, and in this phase, what the eigenvalues do, they will be shifted by an order 1 correction. And the order 1 correction, everything is deterministic, nothing fluctuates. And that's the full spectrum. Now, by the way, since the Hilbert space is 2 to the n dimensional, you know that these eigenvalues of the adjacency matrix are heavily degenerated, and the degeneracy is given by the binomial coefficients. And if you now switch on kind of the random potential, what happens is these degeneracies, they will be lifted, but on the scale of an exponentially small scale. We believe we can only prove that. And there's just the usual kind of second order correction. That's what you would formally get from second order perturbation theory if you do degenerate perturbation theory up to this point. Then there's the other phase, which is the spin glass phase, where what you see is really just the potential. And there's also a correction, which coincides with second order perturbation theory, which at the very tip of the potential is also deterministic, because at the tip of the potential U infinity is just minus beta C times n. So this is then order 1. And there's really a one-to-one correspondence of the eigenvalues of this random matrix with the large deviations, the large negative deviations of the REM. Okay, so, and correspondingly to this picture, if you ask how do the eigenfunctions behave, well, here they are sharply localized, each in its own hole of this REM. That's this golf course hole. And here, they are very close to the old eigenstates. All right, I think I've already kind of stretched your attention a bit too much. Now, let me say the following. This is not only a result about the spectrum. In fact, one of the intentions of why we wanted to prove this is we asked ourselves, now that we have formulas for the free energy, and the free energy is extensive, so there should be corrections to the free energy. Right? And the corrections to the free energy are on order 1. And how do they look like? Are they deterministic? Do they fluctuate? The answer is, it is these terms here by which you can compute the subleading corrections to the free energy in all phases, in the paramagnet, in the spin glass, in the classical sort of paramagnet. And this, in fact, allows you to determine also the fluctuations of the partition function in the spin glass regime. And what are the fluctuations in the spin glass regime? Well, they agree with the classical fluctuations, which were determined in this annals of probability paper by Bouvier, Kokova, and Löwe. And they just shift deterministically. And that's the deterministic shift. And you just insert for u infinity minus beta c times n. Okay, so this is what this analysis on this localization scale all allows you to determine. I think I will spare you sort of a bit the machinery. So maybe kind of as a summary, these are probabilistic problems, and to the experts in the audience, they will know that these transversal magnetic field problems, they have a probabilistic representation. So e to the minus beta h, you can represent as a path integral over a trajectory space where there's a possible process of spin flips. For a long time, I found this very appealing, and then basically what brought all these results to life was to not look at these problems through this probabilistic lens and with these probabilistic techniques. What makes all of the results which I showed you in the last half an hour, namely the quantum parisi formula for this generalized random energy model, and also the localization analysis, what makes this tick, or what's happening in the machine room, are really analytical results. And what's very crucial is kind of cut techniques which allow you to ask questions. So, what happens if I take the hypercube and I now analyze what's happening on a ball in the hypercube of a certain radius? How does the adjacency matrix behave? And what kind of bizarre features does that have? And as it turns out, and that's known, in fact, already to people who work on optimization problems, funnily, so kind of more in computer science, is that if you ask what's the norm of the adjacency matrix, oh, that's an R, sorry, that's a typo here, of just on a ball of radius R on the Hamming cube. Remember, the adjacency matrix on the full Hamming cube, that its norm is n. Right? On a ball, the norm actually is only square root of n. So there is a huge ground state shift if you do confinements. In the picture, coming back to this pinhole thing, where is it? Here. Is that, this kind of adjacency matrix does not really like to localize in these holes. You have to pay kind of a huge price for the kinetic energy. And therefore, essentially, I mean, what happens is that you can think about this random matrix as kind of two separate parts. This does its own thing, and it's mostly determined by the holes, and this does also its own thing. That determines what happens on the rest of the system. And so the spectrum is basically a union of the two. All right, good. So, so if you're really interested in how this is done, I've put up kind of the list of references. The latest work was just posted, and that's this paper where we really analyze the free energy of the quantum random energy model up to order 1 and determine all of the fluctuations in the spin glass regime. Okay, and as I should point out that basically most of these works were done in collaboration with my PhD student Tokyo Manai here in Munich, and the nice little argument about why replica symmetry breaking persists was done in collaboration with Hajo Leschke and Rainer Ruder in Erlangen. Thank you very much.
Thank you very much, Simone, for this very nice talk. And we can have questions and comments. Please raise your hand in the system if you would like to ask a question. Yeah, Michael, please go ahead.
So did I understand correctly that the quantum parisi formula, which you presented, can be intuitively explained by the decomposition of the spectrum into two very different classes of states, as if the Hilbert space is just union of two, and it's a competition between the two sets of states' contribution to the partition function?
Yes, kind of. That's the typical description for a first order phase transition, right? Mm-hmm. And that happens in this quantum random energy model, and in some sense, sort of the way we determined for the generalized random energy model these parisi formulas is by hierarchically peeling off these layers of random energy models. And there is kind of always in this n step replica symmetry breaking models, there's always a first order phase transition where part of the system then just doesn't care anymore about the random potential or the transversal field and does its thing. Flips
so in a way, so the message is that is the message that you can think of the Hilbert spaces consisting of the p states and x space states, as exactly. If these were in different possibilities. Yeah, thank you.
Right. I mean, that's since you mentioned p and x states, I mean, Boris Altschuler was heavily sort of interested in this quantum random energy model, and he coined the term p and x states. Mm-hmm. And more or less, what we did is I'm not claiming that we now proved everything which Altschuler claims about this model, but we have a good understanding that in fact what he states is not so off.
Thank you.
Yes, further questions? Yes, Massimiliano Gubinelli, please.
Very interesting talk. Thanks. I had a curiosity about this, the fact that at the end you commented about probabilistic techniques not being really useful or effective. I mean, can you can you give an idea why it's difficult to see the same behavior? Well, now that you know somehow the answer, no, or the technique that works.
Yes.
Why it's difficult to see it from in the random walk point of view? If you have a,
yes. So see, essentially, if you sort of, I guess you can probably, if we sort of guess what we do, and we cut the hypercube around these large deviations, and you know, on order n, we anyway know that because of, you know, this is because of this result, the cut is only gives an error square root of n, right? So for the free energy, you know, that's as simple as it is. On order 1, of course, maybe that's not good enough, and then you have to really start a localization analysis and make sure that these cuts, where are they, are far enough from the centers, that, you know, the wave function which you get here, this is exponentially small there already. So that you can patch it up, and there's no tunneling and so on. You know, this I found easy to think about and doable, and it's kind of natural if you see this geometry and do a bit of probabilistic estimates, that, you know, these large deviation sites are basically sort of, if you tune up epsilon, we certainly separated, and if, you know, if you go sort of to the small epsilon regime, they may overlap, but then it's manageable. But you have a picture of how things look like, and you also have a picture how this first order picture can arise, namely the Hamiltonian is basically a direct sum of what happens in here and the rest. Right? And that's what you see here. Now, in the path integral, so if you think about sort of that you represent these n Ising spins, and you know, let me line them up, and then beta is this time, and you have these spin flips. You basically perform kind of a random walk in this landscape, and I think what in retrospect sort of what happens, and we can also, you know, in retrospect we can of course feed in the spectral information into the path integral. What happens is that you dash from one large deviation to another. You kind of make a dash. So these paths, sort of, they linger, and then they dash over there, spending very little time over configurations like that. And somehow, I guess, maybe
well, they can stay in one, no? They don't have to go around somehow.
Yeah, they can stay in one
at random.
If they, you know, you have to control sort of that they dash over. But what corresponds to this kind of decoupling, I think, is that they spend very little time over here, and then if they go to the next hole, which is very unlikely, they really go quickly to the next guy.
In this sense, it's reminiscent of Sinai's work in random environment.
Yes, I think this is also, you know, I think is Anton here? I don't think so, right? Anton has this perspective that all this metastability, which is these aging phenomena, which is not kind of this generator here, but where you weight the adjacency matrix according to the usual Glauber dynamics, that you prove aging with these probabilistic techniques. Kind of my dogma is now, I can see all of these things in these models much more simply with my spectral glasses.
Yeah, okay.
So I want to be a bit controversial. And since I largely received an analyst training,
well, I mean, the Dirichlet form is not really probabilistic technique, it's an analytic technique. So maybe Anton would agree with you. I don't know.
So, I think these cutting techniques, which are very natural in spectral theory, I would say we are superior. Of course, in the end, you should be able to translate all that.
Yeah, maybe it's more large deviation for the path integral. I mean, that one should look at.
Yes, but I can tell you the other problems where people spend pages, like this related. It's not random, but quantum Curie-Weiss model, where that's something which we are now looking at, and there are papers by, I think, Crawford, and we're spending, I don't know, 20 pages on large deviations in the path integral to analyze this thing. I think if you look at this spectrally with spectral techniques and operator theory techniques, much more simple.
Good to know then. Thanks.
So maybe can I ask a follow-up question? I mean, since you're using operator and spectral techniques, how about real-time evolution, e to the minus IPH?
Yes. So, right. Good question. In principle, if you know enough about the spectrum, maybe you can certainly, if you so, determine something about e to the minus ITH, as you know. As far as I know, nothing is done in this direction. And what is done, and that's very popular in quantum information, is that you look at adiabatic interpolation. So you have an adiabatic parameter, you have your problem Hamiltonian, that's this U, of which you want to search for the ground state. And then there's, what is it, if you sort of my transversal field, let me call this T, right? Of which you know the ground state, because that's this extended set, you can prepare it in the lab. And at time t equal to 0, you prepare the T ground state and then choose big T, large enough, so that, in this energy landscape where, I draw the spectrum of H of T versus T, right? And I hope that, there's no level crossing, or it can be there's an, over the whole time period, a stable spectral gap. And this was looked at extensively. And what there's a beautiful argument, which is the scrambling argument by Fari and Gutmann, which tells you that these type of Hamiltonians, they typically have a gap, almost gap closing, where the gap is exponentially small. I'm not sure whether I'm explaining myself coherently. So the background is by means of the quantum adiabatic theorem, that the spectral gap is tied to the question, how slow do I have to do this adiabatic evolution so that I always stay in the ground state, right? And what people are, of course, worked up is beating the Grover time. So beating the square root of the phone book, right? Which is in this case 2 to the n. And once you have a gap, almost gap closing, which is exponentially small, and you have to this determines sort of the slowness of this adiabatic process. And there's a beautiful argument why you cannot really beat the Grover time in all kinds of problems which are permutation invariant. So from there, you actually know that there is kind of this first order phase transition in the ground state. That's kind of how physicists would argue that. And this was extensively studied, and this is actually mathematically, completely kosher.
Okay.
Other than that, as I said, somehow, this is a very kind of mathematically a very new field.
Okay.
So, you're welcome if you sort of contribute something to the real-time evolution.
Okay, thank you. Are there any further questions?
Oh, everything is called T now. That's interesting.
Yes.
Yeah, that's good.
So I don't see any further questions. Thank you very much for this talk with so many nice results, nicely presented. And thanks everyone for joining, and see you next time in about a month.
Thank you.
Thanks for your attention, and thanks for inviting me.
Thank you.
Pleasure.